and get started also. All right. So hello, everybody. My name is Sam Robinson. I'm an assistant teaching professor in the UW Department of Chemistry, and I want to thank you all for joining us today for our seminar. We're thrilled to be welcoming Professor Alena Moon with us this afternoon. To start today, we do want to hear how you heard about our seminar, so I'm going to put our poll in the chat for you. If you can all log in there to let us know how you heard about us.
I think this survey is the one to use.
Oh,
yes.
Perfect.
I think that's what we did last time.
All right. And before I introduce our speaker, I want us to take a moment to acknowledge, as the University of Washington and attendees from other institutions, the Coast Salish peoples of this land, which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Our speaker today is Professor Alena Moon. She completed her undergraduate degree in Arkansas at John Brown University. She then continued her education in Marcy Towns Group at Purdue University, and then also did postdoc work with Ginger Schultz at the University of Michigan in Ann Arbor. She has since joined the faculty at the University of Nebraska in Lincoln, where her group is looking at how students develop deep understanding of science practices, what factors impact students' argumentation skills, and I believe today she's planning to tell us about recent work that's centered around the idea that's at the very center of an education in chemistry. Her group has probed how we develop our own understandings of the interaction between light and matter, from when students are initially introduced to the concept to more sophisticated insights as graduate students and beyond. And so with that, I will turn things over to Alena, and welcome everyone.
Thank you for the lovely introduction, and thank you so much for inviting me. I'm in the process of doing my 4th year evaluation, which is like our little pre-mock tenure thing. And so I'm actually really feeling like we've done a lot of work, and I'm so excited to get to share it with people. So we'll get to it. Maybe. Okay. All right. So not just chemists, but really scientists use light pretty ubiquitously, right? And in chemistry, we really care about its capacity to elucidate the structure of matter, and give us insight into molecules. But when we kind of zoom out and think about this big picture, we care a lot about how we actually harness and use this energy, and ultimately how we kind of model nature's really excellent mechanism. So we know light is important, but the reality is that it's really weird, okay? And part of what makes light kind of weird is that all people, all of our learners, are developing these ideas about how it works based on what they see. So they're interacting with visible light, and they're interacting with the world, and they develop these ideas. And then they come into our Gen Chem class, and we're like, take those ideas, and we're just going to use this on this scale that you've never thought of, right? And so my group cares a lot about how students undergo this transition, how they make this transition from conceptions of light that are based on those experiences, so interactions with visible light and thinking about it classically, to thinking about the quantum scale, which involves thinking about invisible light and applying it to the atomic molecular level. And so this is a big transition, and it happens over a really long period of time, right? Which is why probably chemistry curricula are organized to kind of keep hitting at some of the components of these concepts, right? And so our group has thought about approaching this with a learning progression. And I popped one up here from some of our colleagues in Italy who have done one for quantum mechanics, another real big idea. And the cool thing about learning progressions is that they represent, for a real big idea over a long period of time, what are the increasingly sophisticated ways someone can reason about that concept, right? And the other really cool thing about a learning progression is that on a smaller scale, it affords a very cool approach to assessment and thinking about curriculum. And we're going to spend a little bit of time here because light matter interactions is too big. And so in order to start, we said, okay, let's just think about how chemistry students reason about light. And let's approach it with this construct modeling approach. And this approach is super cool. The key feature of this approach is that you start with this robust model of cognition that represents how students know things in that domain, in our case, about the nature of light. And then you design assessments that give you information about what they know. And then you can evaluate those assessments or responses to those assessments and build really cool measurement models. So you end up being able to make really cool claims about what students know based off of this. The issue, though, to take this approach that I really believe is so helpful is that we really know nothing. So when it comes to making this model of cognition and like figuring out how students represent knowledge in this domain, we just don't really have anything. So that's where my group has started. Let's just figure out what students think about light. And to do so, good, okay. To do so, we have investigated this qualitatively, right? So that means we have interviewed a lot of students, a lot of chemistry students across a lot of levels about two fundamental experiments. So in the general chemistry curriculum, we typically introduce these experiments to teach, typically we use this photoelectric effect to be like, oh my gosh, light behaves like a particle, what's happening? And then we kind of introduce interference to be like, oh my gosh, matter is also doing wavy things. So we wanted to use these experiments that students touch on in general chemistry, but like none of us really get to spend as much time talking through these experiments as we would like, right? To really appreciate the implications. To tease out their ideas about particle, wave behavior, and then duality, right? And so I'm going to walk you through kind of what we found in both of these experiments and how we've integrated it all together to build these models of how students learn these concepts. In order to understand how we approached our interviews, I have more theory for you. I theory really hard. Apparently too hard, according to my recent career reviews. Okay, so we rely on a theory called knowledge in pieces. This basically asserts that in response to a problem, students will activate whatever resources, not just students, like humans will activate whatever resources they need to make sense of that problem, right? And this can vary, right, based on context. But one of the cool things is that it sort of shifts us away, and this is really in line with the learning progressions approach, is it shifts us away from characterizing their knowledge as correct or incorrect and more towards productive or unproductive, so that we start thinking about sort of how we use these ideas. And there are a few key elements of this knowledge in pieces. This one called phenomenological primitives. It's a big one, but basically, as I alluded to earlier, people navigate the world and they develop ideas about how the world works based on that navigation, right? And so this theory emerged from physics, where you can imagine that students' interactions with things in real life would impact how they learn classical mechanics, right? Like they're just like, okay, things move this way. And so this is a specific kind of knowledge element that a student could activate. And it's it's sort of the irreducible knowledge element. So students can't explain it, they just use it. And then we have kind of a whole host of other kinds of knowledge fragments. And the other key piece that this theory helps us explain is contextuality, which means that the resources a student activates in one context may not be the same as what they activate in another context, right? So this kind of helps us explain that. This is really useful for representing ideas that are perhaps a little bit more fragmented, right? But we know that as learners develop and enrich these resources and activation of resources, they can develop more cohesive concepts, right? And so on the other end, on the more sophisticated end, we would describe these concepts as coordination classes. And we can think about this as sort of a constellation of resources that a learner can activate at an appropriate time. And these constellations are made of extractions where a student will make some observation about something that they're looking at, and then they draw conclusions about it, right? And their ability to invoke this constellation of concepts to do so, in order to be a coordination class, must have span, which means they must apply this coordination class in appropriate contexts. And it must have alignment. Alignment, I'm sorry, I keep getting stuck. Sorry. Okay, anyways, it must have alignment where a student recognizes the components in any given situation that are relevant to the coordination class. So those are the ideas that we are taking with us to investigate students' ideas. Let us start with the photoelectric effect. So we used this very simple representation, but we really milked it for all it's worth because it actually captures a lot of really cool information. And the overarching question was just, how are they reasoning about the photoelectric effect? And in order to do these interviews, we ended up, so we did them cross-sectionally, like I said. We ended up asking them some easy peasy warm-up questions where we would put, I think we printed out some relationship between speed of light and wavelength and said, what are these variables? How are they related? And the warm-up questions functioned like the warm-up. So the students are like, yeah, I know these equations, I'm feeling good. Then we offered up this representation without any electrons or ejected electrons emitted or represented. And we just said, what do you think will happen? Okay, and why do you think that will happen? It got a lot harder. And then we showed them the representation with the ejected electrons represented and asked them to explain what was going on. Finally, we had students evaluate the model of light that they used to explain the outcome. This part was rough, so we didn't even get there with all of our students. So we did a bunch of interviews, and we ended up trying to use our framework to think through what kinds of things are they telling us about, are they explaining, organizing those different ideas that they're talking about according to this theoretical structure that I just explained. And then finally, we took all of this and we organized it hierarchically according to how productive their explanation of the photoelectric effect was. Could they explain the outcome mechanistically? And this resulted in 3 levels. This resulted in 3 levels. So I'm just going to show you our level. So at our less sophisticated level, we had students coming in with limited or absent prior knowledge. I don't think that one's really a surprise, and pretty inconsistent use of prior knowledge. Some of the interesting things here, though, was we saw a focus on visible light and wave behavior, even to explain things that were not useful for explaining. And then really inconsistent predictions. So even across, you saw different frequencies shined on the representation I showed, even inconsistent across the different frequencies. However, we saw this developmental class of students where they were pretty good with the relevant relationships that they would need to think about this. But then this new thing popped up with these students, is they just got really uncomfortable with the idea of electrons leaving a metal surface. And that resulted in some kind of wonky ideas about the electron and the photon, where they conflated them. But here's another cool thing that we saw in this developmental class is they started to try and reconcile wave and particle behavior. It wasn't done great, but they started, right? In contrast to our students who were just like waves for days. And they also were able to make correct predictions, but we just didn't see a mechanism there. So our most sophisticated responses had the things that you would expect, like they could tap into the knowledge that was useful here. And one unique thing kind of popped up for what we are calling our coordinated class is they really effectively distinguished between continuous and discrete variables, which was really at the heart of this wave first particle behavior. So it was really fruitful for these interviews. And then we saw much more successful integration of wave and particle behavior and the mechanism. So I'm going to kind of walk you through some examples of all of these different students and try and elucidate some of these differences. The first person I'm going to show you is Kate, and it's a chunk of text, but look at the ideas that she relies on. So there's actually really cool things going on here. Ultimately, Kate completely over relies on some physical experiences that aren't super relevant, but she also sees that light excites electrons, right? So this is an example of an over reliance on physical experiences and intuitions, even when we might not expect it, but this is something that could be leveraged instructionally a little bit better, right? To build on this idea of light exciting electrons. The other piece that we saw was in the absence of sort of relevant prior knowledge, that they would fall back on these really intuitive mechanisms for how things happen to explain the outcome. And Candice does this. So I'll give you a second. So we start super strong, recognizing where electrons come from. Except for when we prompt for an explanation of this, she ends up relying on this sort of substitution mechanism to rationalize that there must be electrons in the light that are like physically kicking out sort of these electrons from the metal. So this would be an example of really context dependent, fruitful reasoning, but it just didn't make it throughout the whole process. Okay, so these were examples of some of the more fragmented ideas we saw, but we did see students start showing coordination. So I'll give you a second with Tom. So Tom also does some things that we're excited about. He starts by invoking like chemist's favorite p-prem, which is more is more, the idea that more of something is going to lead to more of some effect, right? And we're like, no, not more is more. And so we probe a little bit further, and he corrects himself. And he starts raising ideas or aligning with prior knowledge that's really useful here, right? And so this was a way that we saw students drawing on these correct relationships in more relevant ways. One other feature of the developmental class was that they were rather coordinated, whether or not that was the best way to be thinking about the problem. And I'm going to show you sort of, they would make things fit how the framework that they wanted it to fit, right? And this is important because it represents some connectedness between their ideas. But ultimately, in the case of Tony, it didn't serve him super well. And so I'm going to show you, it's kind of a messy quote, but imagine a two-level system in which an electron is being promoted. That's how Tony's thinking. And he's going to make it fit the photoelectric effect. So this is just a small snippet of Tony's commitment to this two-level system for explaining this phenomenon. It was used throughout. But what we see, again, really promising start. We promote an electron. And then Tony tries to use emission concepts to explain, and it just falls apart. It falls apart, and that's what gives rise to this conflation of the electron and the photon. So what we saw was alignment and coordination of ideas, but just with ideas that didn't serve Tony very well, right? Okay, and then as we moved to our more coordinated students, I said that one of the cool things was their differentiation between continuous and discrete variables, and just get ready for Ruby's explanation. So we were pretty pumped to get this from Ruby. The other cool thing is that, again, this is just a snippet. So Ruby applied this reasoning to make sense of the whole phenomenon, which is really amazing. The other thing that we saw in our coordinated class was sort of the best version of being able to coordinate relevant ideas, right? And so let me show you Philip, who did a little bit of reflecting and resetting. So Philip starts by making some inferences about what he's looking at. They're fine, but we weren't completely getting where Philip was coming from. So we probe a little bit further. And then he sort of reveals that he was thinking on a scale really different than what we were exploring, and then corrects, aligns with prior knowledge it's really useful for him, and then makes another observation and inference that is far more productive, right? And so this kind of represents some of the continuum we saw with reasoning about particulate behavior, especially in the context of the photoelectric effect. So now let us jump into the double slit experiment. We again here tried to explore cross-sectionally. We did just because of when we collected this data, there were very few physical chemistry students. And the distinction between the general chemistry students and the general chemistry majors was that we offer a separate Gen Chem series for chemistry majors, and physics majors take it, some biochemistry majors take it, some chemie majors take it. So, so for anyone who cares, the physics kids just hit this out of the park. Okay. We did these interviews unlike, I've never done interviews like this. We used PhET simulations. So we would have the computer with us. A student would sit across the table, and then we would walk through different simulations doing the same sort of predict, observe, explain type thing. We started with a continuous light source with no barriers, just to figure out what's going on. We introduced a barrier with a single slit and then the screen. And then similarly for the double slit, we introduced 2 slits and then a screen. So this is the progression that students went through. And we saw really similar breakdown into sort of 3 categories, representing real fragmented on one end and more coordinated on the other end. And our more fragmented students here still demonstrated an over-reliance on visible light. And you'll see the way that this comes up in double slit. Then the thing that kind of shook out with the developmental class was they could get on board with constructive interference and use that selectively, not on board with destructive interference. And similarly struggled to kind of put together a mechanism. And then here with our more coordinated students, we saw kind of reasoning from constructive and destructive interference together to generate this mechanism. So let me give you a taste of how these students reasoned. Here is reasoning in what we would call fragmented with a single slit. So we were a bit taken aback by the invocation of shadows, but this was used frequently throughout the interviews. So students explained what light did when it met a barrier with shadows. And so we're like, well, how will this translate to the double slit? So again, here we see the invocation of a shadow to explain, really, in addition to the blurriness, any not lit regions on the screen, right? Shadows were what explained that. So we're seeing an over-reliance on intuition. Okay, and then in our developmental kiddos, so we're feeling pretty pumped here. This is to be able to think about nodes and antinodes is a really sophisticated idea, right? To think about light that way. And we definitely did not see it across the board. Then the student falls back on really intuitive mechanisms for explaining. So like really cool thinking about how the light is working, like what the wave means, but then to connect it with the pattern that they observed, we saw really classical ideas, one with the pool balls, and sort of intuitive ideas. And it reveals some of the context dependency, even of these really productive concepts we saw, right? In the more coordinated end, we see really cool recognition of what concepts will help them and what won't. So using the language of our theory introduced earlier, we would say that this student sort of displaced ideas that weren't serving them, right? And that was the recognizing that interference wasn't going to be productive for thinking about this single slit. And then we saw pretty productive explanations and predictions. So this sort of represents kind of what we're shooting for, right? It would be productive to see students reasoning about light interfering and how that gives rise to what we observe on the screen. Okay, so I had said earlier that we wanted to kind of take all of these interviews and start thinking about how they thought about wave particle duality. And we got some cool differences. So on one end, we see relying heavily on classical behavior. So real, I mean, like asteroids hitting other planets. And then again, orbit, like the Bohr model lives forever. So that's not surprising here. So real classical ideas about light. As I said, some of our developmental learners started trying to reconcile these behaviors. And one of the ways that this manifested itself pretty frequently was through this sort of model, where the learners would argue that the wave is comprised of particles. And the cool thing is when we dipped into the physics literature to be like, are you all seeing this? We found really similar representations in the physics literature. So we're definitely not the first to start seeing this attempt at reconciliation. And then finally, we see some pretty sophisticated explanations. So in order to do the approach to assessment that I introduced earlier, we have to deconstruct wave particle duality or the nature of light, which is a pretty big idea, into specific progress variables. And here's how we went about it. It is a very non-trivial task. Basically, analytically, we identify these specific variables about which we observed variation in sophistication of reasoning. And the way that this shook out was 4 progress variables: particle behavior, contextualized in the photoelectric effect like we saw, general wave behavior. So you can imagine that the first 2 simulations were probably helped us think about that, interference, and then duality. And so for each of these, we have a construct map. You may not read it. You don't necessarily have to read it all. But what we have is students' ideas ranging from our lowest level, which would be particles of light having mass and force, super classical particles, all the way to our more sophisticated, being that particles of light are discrete units of energy. And then we also have these kind of common errors that we think are getting resolved as students might move from sort of additive energy transfer to discrete energy transfer, for example. And here's an example of what a level 1 response would look like on this construct map. So if we saw this reasoning from a student, we would code it as a level 1 from this construct map. Here is reasoning about wave behavior. So on the lowest level, you see the use of shadows and visible light to explain wave behavior, all the way to the most sophisticated, which is recognizing that waves have nodes and antinodes. And that's what you see represented here, this quote. So if we were to see an excerpt like this, we would just code it as a 4. Here is our construct map for interference. So we see still shadow ideas, but basically really broad light can interact and add together, but no connection to what we observe, all the way to constructive and destructive interference giving rise to a repeating interference pattern. And then the level 2 here was kind of interesting because what we see is reliance on constructive and destructive interference, but selectively. So it only explains some regions on a screen that we might observe. And then finally, here's how we thought about duality. There was just no effort at reconciling the behaviors or thinking about how they could go together on the lowest level. But on the highest level, we saw recognition that the behaviors, that wave and particle properties are both real, right? And that the experimental setup is going to dictate what we observe. And then we ended up splitting. This was a hard one to think through. We ended up splitting this effort at combining them into a lower level of waves being comprised of particles, which is represented by this quote, and then particles moving in a wave trajectory. And I'll give you a second with this quote and then try and explain. So this quote and this idea, we thought that the learner was reasoning about wave and particle behavior on different scales, right? Because the particle was the small part that made up the wave part that they observed, right? Whereas in contrast, our level 2 students, we saw assigning wave properties to particles. And we were like, well, that's a pretty productive thing to do in quantum mechanics. So we are going to recognize sort of the sophistication of that by assigning this wave trajectory to particles. Okay, so we have these 4 construct maps, and we want to start designing some assessments to help us diagnose and measure students' ideas, right? And this approach to assessment is really cool. I'm still learning it, but it's very cool. So we have these construct maps, and then what happens is they map explicitly onto the response options for a multiple choice item. So traditionally, you think about a multiple choice as having a correct answer and then distractors, right? But that's not what an item like this would tell us. So instead, it would point to how many level 1, how many level 2 students we have, right? or responses. And then we model this assessment using item response theory. And I'm showing you an item characteristic curve, which here's the cool thing about this approach. What it shows here is the probability of selecting a specific response, right? As a function of a specific ability range. And so what you see here is that for a given ability range, a response is most probable. This is like what you want an item characteristic curve to look like, not what all of ours look like. Okay. So but it's just kind of a cool glimpse into the kind of information you can get from it. So here's an example of an assessment item where you have student responses and then how it made it into the item. And we really worked to conserve student terminology and ideas in these items so that students were selecting the thing that they thought made the most sense to them, right? We have developed multiple items for each of these construct maps now. And I'm going to show you a little bit of preliminary data. It's like very pilot. But we administered this assessment to general chemistry students following instruction about, like basically following examination over the quantum mechanics chapter in general chemistry. And the really cool thing, I mean, there's still more to explore here, but what's really cool is we're seeing representation of student responses across all of these levels, right? So what we can conclude here is that these response options are describing some students' ideas, right? That they're appealing to some students. So we think we're onto something for modeling students' ideas this way. We also have a lot of responses that are helping us revise the instrument because, like I said, not all the item characteristic curves were as pretty as the one I showed. So big picture, we think we're onto something with modeling students' ideas this way on a continuum. So we plan on continuing. And really what we're learning is that we're just sort of scratching the surface of how students reason about light. But, and I don't want to overpromise, stay tuned because we have just started. So I sort of presented on a lot of really conceptual ideas about light. And we want to start figuring out how students think about spectroscopy. So we have conducted a whole bunch of interviews with students about UVVis spectra, thinking it's one where students would be interacting with it across levels. So we get to start building these models of how students interact with spectra, which is pretty exciting. So let me go ahead and acknowledge the people that did this. So Morgan Balabanoff is my ex-postdoc. She abandoned me to start her independent career at the University of Louisville. She's in the bottom right. And she's a queen. You should follow her work. And then second from the top left is Hayan, who is the graduate student who's taken over this project. And he's taken on quite a project for his first year. So wish him luck. But yeah, so that's just the excellent team that does everything. And with that, I'm happy to take any questions. I know I went a little fast, so I'm sorry.
I think that was wonderful. I think that in this small of a group, it's probably easiest if people just either raise their hand or just unmute themselves and go ahead and ask what questions you have. Go ahead, Anne.
This is actually Ann and Jacob. Although Jacob seems to be in two places. Really interesting talk. The thing that kind of struck me was some of the answers, I'll refer to them as sort of the Hermione Granger answers, that a student has read the book and memorized the words in the text and may not really fully have digested their meaning. And how do you differentiate the sort of textbook answer from really having the deeper understanding, which you're implying by the level 3 or level 4 in some of this?
Mm-hmm. So I would say that it's the way that we do that is through interviews. So the cool affordance of interviews is that we interact with this reasoning in real time. And the reality is that when they sort of have that level of reasoning about a concept, they run into limitations really quickly in an interview, and we can show that. So I would say that's how we used the interviews to determine when ideas were being held at what you might call a real surface level versus them being able to employ those ideas to explain phenomena. The way that we tried to, well, okay, so that's how we would capture it through the interviews. So then I would say that we worked really hard to try and build the construct maps to capture those differences. And so when a student selects a certain response, I think that these items would be sensitive to a student having a real surface level, like that would map onto a level, and we could determine that that's sort of what they were operating with based on this. That's what I would say. I'm trying to think if there are other sort of conclusions we could draw from what they select. The other thing that we're doing is interviewing, and this analysis is ongoing, but we're interviewing students after they complete the assessment as sort of an extra check, like, are they thinking about these things the way we think they're thinking about these things? And those interviews are ongoing. So I will have way more confirmative answers shortly.
No, thank you. I mean, it's hard when you look at the answer to multiple choice. It's really hard. You don't have the EEG to tell you what's really going on in their heads.
Right.
So it's, as I said, I certainly see, I'm teaching honors right now, and you certainly
Okay.
see a number of students who just have the book memorized,
Yeah.
but haven't really internalized what it all means. So if you word the question just right, they'll know what the right answer is. They may not understand why it's right, but they'll be able to identify it by more of a pattern recognition at some level than really the level of understanding that we're hoping they'll have.
That's true.
I'll jump in as sort of a follow-on to that. I was really curious if your pool of students were all at the same university, if they had taken the same instructors for these classes, or if it's across instructors, because I think we've been talking about or throwing around this idea of like, oh, what if we give common final exams for Gen Chem? Like, this seems like a great way to make sure we're removing that sort of like instructor bias, or to sort of compare across classes. But just the vocab that I use to talk to my students might be different than the vocab Anne is using to talk to her students. And so curious if that sort of predisposition for using one set of terminology over another shines through in this.
So the answer is we can't speak to whether it shines through. It is undoubtedly there. And I would say that that's a pretty significant limitation to my approach to this work. I'm really confident that the model captures variation in student reasoning really effectively. But I cannot say at all how instruction impacts where a student might sit on any given spectrum. So our approaches are to just interview students at other campuses and administer sort of the measures at other campuses too, because it was definitely all collected here. There are definitely differences in instructors that we're just not able to account for. So. it's really hard for doing this kind of work because like ideally, right, what you want is some student that comes in as a freshman. What you want is like 100 students that come in as a freshman, and then you track them all the way through their senior year, and you have such brilliant longitudinal data, but you can't collect data like that. And so sort of the best approach we've come up with is to do things cross-sectionally and try to elicit the variation without attributing it to specific levels, right? So we're not going to say that a senior physical chemistry student who's been through quantum will have X amount of ideas, right? We're just saying, here is what was a more sophisticated idea. And that's what we got.
I think it's really awesome work. I think
Thanks.
I really like the idea of being able to map the multiple choice items onto levels of understanding. I do worry about Anne's point about like, oh, you just have somebody who's got the right vocab words coming out of the textbook. It maybe gets easier and easier to pick that right answer. But I think that it's still, yeah, I think it's an amazing idea.
I think too, and we have to actually, my grad student has to actually like play with this, but I think we could speak to this with the consistency with which they choose certain level responses for an entire progress variable. So, and that's sort of an open question, like, is there consistency or do students? So I will look into that too and see if we can't try and answer or speak to it at least.
Go ahead.
Go for it.
Yes. Hi, my name is Shady. I'm a grad student.
Hi.
Thank you for good and hard work. And I would like to actually make this as a start for like a good way of teaching. I had a class. The instructor was literally saying and writing basic things in science. That was in a grad school recently. The book was all about physics. Yeah, I'm a grad school in chemistry. The homework kind of like related, but the exams has no relation to what's in the class or in the book. So the book saying something, the class very basics, that the exams is very hard. Overall, I passed this class. I'm not criticizing, but for the next year, for the next generation and stuff like that, we need to have a good way of teaching. You cannot take the student to a class, getting the basic thing, ask him to get a book, has nothing to do with that. 10% of the book, literally, I gave from it. Exam about something else. So please do others work on stuff like that. Send the message to how we can gain from the class, from the exam, from the homework. It is not just, I get a degree, let's go out. I'm a doctor, I'm an instructor. So please make it as a start to a good teaching. There is, I've studied abroad. I'm originally from overseas. I had a bachelor degree from there. I had a associate degree here. I work in healthcare field. I'm going to grad school. I've seen tons of wave teachings. in 2 different countries, 2 different cultures. Good teaching, good instructions, make a good student. Thank you.
Yeah, so you said a lot. I'm trying to think of the
I
best,
know,
which chunks
know,
to sort of bite off.
let's focus on something related to what you said. It's how we can make statistics help students, help the way of teaching,
Right,
help deliver the message.
right. Yeah, so one of the cool sort of features of this approach is just how deeply aligned what we know about what students can do is with how we assess students and then how we draw conclusions about them. And that really, we know that that alignment is essential to good instruction, right? So I do think this specific approach to assessment and thinking about students lends itself really well to sort of best practices for instruction and assessment.
Are there other questions or comments? Well, since we're coming to the end of our hour, I guess I will thank everybody for joining us today. And we really appreciate your time with us, Alena. This has been a really excellent
Thank you for having me.
set of questions to think about and directions to go forward. Thanks so much, everyone.